from CNRS in France, and Antoine will tell us about quantum magnetism in dipolar Rydberg atom arrays.
All right, so many thanks. So good morning, everyone. So first, I'd like to thank the organizers, obviously, for the invitations and also for putting together this meeting where we combine different fields related to quantum simulation and quantum computing and algorithms. So indeed, what I'm going to discuss are two experiments that we've done recently where we studied quantum magnetism using dipolar Rydberg atom arrays. So this is our group at the Institut d'Optique. So the Institut d'Optique is actually located not quite in Paris, but 20 kilometers south of Paris on the campus of Université Paris-Saclay. So this is our group, and what is very important to us now is that we have a lot of collaboration with theorists, specialists of quantum matter physics or quantum information, and so I will show how they intervene as we move on. So with this crowd of people, we actually have three projects that we study, and they are all related to this idea of building a synthetic quantum system in order to study many-body properties of this system. So there is this tunable arrays of individual Rydberg atoms, which I'm going to discuss, but we also have two other projects, one where we take a small atomic cloud, very dense. We send light on this cloud, and so the light polarizes the atoms. The dipoles will interact if the cloud is dense enough, and that's an example of a dissipative system. And we have also another experiment where we try to combine the physics that we study here with this light-induced interaction with the tools that we have developed for the tunable arrays of Rydberg atoms. So this is with dysprosium, and this is led in our group by Igor. All right, so I don't think that I need to introduce too much the platform. It has been done yesterday by Misha. So actually, this is something that started now 25 years ago at the Institut d'Optique with the pioneering work of Philippe Granger, who was the very first one to trap a single atom in a tweezer. So a tweezer, this is a laser beam that you focus as tightly as possible, and that acts as a trap for ultra-cooled, cold atoms, so laser-cooled atoms. So there were lots of developments over the years that we did in our group, starting from 2001 to essentially now. And the basic idea is that you can observe those atoms by just making them fluoresce when they are trapped in this tweezer, and we can arrange them in various geometries. So those are examples of geometries that we could prepare in our group. And so as of today, now, at least for us, the record is about 1,000 atoms. And as Misha showed, this platform now is able to manipulate nearly 1,000 atoms, or even larger. So those atoms are very far from each other, and so it means that in order for them to interact, far meaning a few micrometers, so in order for them to interact, we need to excite them and to enhance the interactions, and we do that by promoting them to Rydberg states, which have two important properties. The first property is that when you are in this high-lying state, the lifetime of the state is much longer than if you are on a low-lying line, typically a few hundreds of microseconds. So it doesn't look like a lot of time, but as you will see in a minute, it's long enough to do coherent many-body physics. And the second very important feature is as these Rydberg atoms corresponds to an electron very far from the nucleus, the dipole interactions can be very large because the plus and minus charge are very strong, which induces large dipole. So the consequence of that is that these interactions, if you want an order of magnitude for two atoms separated by about 10 micrometers, the interaction is on the order of a few megahertz. So megahertz means that this is the, I put them in this unit because it's the inverse of this strength, which gives the typical time scale over which you can look at physics, which is driven by the interactions. So this physics is therefore sub-microsecond, and that's the reason why this lifetime, although not very long, is still long enough in order to observe coherent physics. Of course, at some point, it's kind of a limitations. I mean, Misha also discussed that in the context of the fidelity of gates, and the fact that they have a finite lifetime is a limitation of the platform. All right, so everything we're going to do, it's different from what Misha explained. We're going to do everything in the Rydberg manifold. So essentially, we have a laser beam with which we excite the atoms that are initially in their ground state up to a given Rydberg state, the state 60s. The exact state doesn't really matter. And so everything now is going to happen by mapping our system on these two states. So it will be a two-level system, spin up and spin down. And so these two states can be manipulated easily by microwaves. because there is a strong dipole matrix element. So this is an example of a Rabi oscillations on this microwave transition around 17 gigahertz, and this is done on a single atom. So as you can see, there is nearly no damping. So you can manipulate those Rydberg states with a high fidelity, at least at a single particle level. From the point of view of the interaction, what we're going to consider is what is called the flip-flop or resonant dipole interactions. So this is the situation where one of the two atoms is prepared, let's say in state P, the other one being in state S, and they're going to exchange by the dipolar energy of a virtual photon, if you wish. And so this can be measured directly on two atoms. You prepare one in spin up, the other one in spin down, and you see, as a function of time, you measure the state of each of the atoms, and you observe that indeed they exchange coherently their state. Coherently is a bit of an overstatement. As you can see here, there is some damping, and the damping comes from the fact, essentially, that the atoms are not trapped when they are in the Rydberg state. So this is not an intrinsic limitation. It can be done. It just turns out that for simplicity, in our case, so far, we do not trap them. So this implements directly this sigma plus sigma minus Hamiltonian, this flip-flop Hamiltonian, which actually theorists usually prefer to write as an XX plus a YY Hamiltonian. So with this platform, we're going to look at two problems. The first one is going to be what happens when you place a dipolar magnet out of equilibrium, and as you will see, it leads to interesting modification of the dispersion relation due to the dipolar tail of the interactions, which is not something which has been known for centuries, and this is something that was predicted about 10 years ago and never observed so far. And the second thing, I will extend the use of this dipolar interaction not to just two states, as I just explained you, but to a third state. And with that, we're going to be able to observe and to study doped magnetism by implementing what is called a TG model. So let me start with these out-of-equilibrium dipolar magnets on the measurement of the dispersion relation. So this is a work that we've done in collaboration with Norm Yao in Harvard, who provided the theoretical support, as well as Tommaso Rosilde and Fabio Mezzacapo in Lyon. Okay, so the question we're going to ask is the following. So we just take an ensemble of spin 1/2 particles, we pin them in space, they interact through these sigma plus sigma minus Hamiltonian, which is relevant to study magnetism, as we discussed, but also the transport of excitations in systems. And what is special here is the fact that this is a 1/r³ interaction. So this is a very important point because first, it's relevant to many different platforms. We've heard about Rydberg. I just discussed that. But also, if you want to look at defects in solid, they interact by the magnetic interaction. It's a 1/r³. Magnetic atoms that people manipulate and are very popular in the field of ultra-cold atoms, chromium, erbium, dysprosium, are also 1/r³ type of interaction. And the molecules also are example of objects that interact by a dipolar interactions. And there is a lot of progress with the molecules, and that now have reached a lot of maturity. So the reason why this 1/r³ is interesting is because it brings immediately something which usually is hard to simulate, at least for large systems. It brings frustration. So just to illustrate that, let's consider this example of a square where you have an antiferromagnetic interaction. So the antiferromagnetic interaction is going to favor an antiferromagnetic ordering along all the edge of the square, which leads then to a ferromagnetic ordering along the diagonal. But this ferromagnetic ordering along the diagonal is in competition with the natural antiferromagnetic that you have due to the interactions. Obviously, it's weaker, this antiferromagnetic destabilization, but still it's large enough on a square to destabilize the order, as I will show you. So now we're going to see what's the consequence of having this dipolar interaction on the out-of-equilibrium properties of this system. So essentially, when you have an ensemble of spins that are coupled, the low-lying excitations can usually be described as spin waves. It's not always the case, but at least on the square, this is the case. So essentially, what you look is what is the evolution of a spin component, and you just try to impose a spin wave, and you look at the relation between the frequency of the spin wave and the momentum. So this is the dispersion relation. So it turns out that you can do some linear spin wave dispersion theory, which you have to be a bit careful. I mean, it may not converge, so there are technicalities here. But essentially, the result is that the frequency of the spin wave is related to the Fourier transform of the interactions. So the interaction is this 1/r³, and it will be different whether you got ferro or antiferromagnetic interactions. So now if you just unwrap this formula and plug it and look at the scaling, what you find out is that if you add nearest neighbor interaction, so not the case I'm discussing, but nearest neighbor interaction, whether it's ferro or antiferro, you will always find that the dispersion relation is linear as a function of Q for the XY model, Q being the quasi-momentum. So on the contrary, when you have a dipolar interaction, the dipolar 1/r cubed does modify the ferromagnetic dispersion relation. It goes from a linear dispersion relation to a square root of Q dispersion relation, which is a bit of a pathological situation because it corresponds to a diverging group velocity at a low momentum. On the other hand, the antiferromagnetic case is not modified by this long-range interaction, and that precisely comes from the frustration that actually destabilizes the order, or so to speak, makes the interaction effectively short-range. So the consequence is this 1/r cubed is interesting, and once again, the point I want to emphasize that all this has been predicted in 2012, and it's not something which is known for so long. So now, how can we measure this dispersion relation? So the idea here is to place the system out of equilibrium and apply what is called quench spectroscopy method. And I will try to contrast it to what is done in condensed matter physics. So traditionally in condensed matter physics, what you do, you prepare the ground state of the system and you perturb it above the ground state in order to access the low-lying excitations. Here it's done much more violently, in a sense. We're going to measure the dynamics after a quench, and this quench will prepare a mean field approximation of the ground state. So essentially that means that the state we prepare is the true ground state plus a little bit of something, and the little bit of something are precisely the low-lying excitation, which is to say the spin waves. And so the true ground state is a superposition of the mean field ground state plus the spin waves. So the consequence of this, and the reason why it's interesting to do it, is because it's easy experimentally to prepare the mean field ground state of the system. I will show you why and how we do that, but essentially the idea is that a mean field approximation of the ground state in the X is simply the ferromagnetic ordering in the XY plane for the ferromagnetic case, or the interferromagnetic ordering, so the Néel state, in the XY plane. So these are easy to prepare because those are product state. So essentially, they require only single particle manipulations. So now, this state is going to evolve as a function of time, and of course, the spin wave part is going to evolve with the frequencies that are related to the dispersion relation. So now it turns out that if you calculate what is called the time-dependent structure factor, which is not exactly the quantity that people measure in condensed with neutron scattering, it's a different quantity, it is essentially the Fourier transform of the ZZ correlation as a function of time. Okay, so you do that, and this Fourier transform is directly related to the dispersion relation. So essentially, it will show an oscillation at twice the frequency of the spin wave you want to measure when you've got the Fourier transform. So this is this method that we're going to apply here. So let's do that. So we take a 10 by 10 array, which is prepared with the atoms separated by about 15 micrometers. Initially, all the atoms are along the spins are pointing along the Z axis, which is our quantization axis, and at some point we apply a microwave pulse, a pi/2 pulse, in order to prepare all of them in a superposition of up plus down, which is to say in the X state along the X axis in the XY plane. And so now we measure, as a function of time, how the correlations, the ZZ correlations, evolve in the system. So it means that we measure on each realization of the experiment the state of each of the atoms. We can do that because, of course, we can resolve and assess the state of each of the atoms. And we measure the correlation. So this is a 2D map of these correlations. So initially nothing special, but as time goes on, you observe that the correlation evolves as a function of time. So now we're going to make this two-dimensional plot a single-dimensional one just by integrated at a given distance d from the center. So once again, this map is the probability that if you have a spin up, say, at a given site, you've got another spin up at another site. Blue means negative correlation, red means positive correlations. So what we observe when we make this 2D plot, a one-dimensional one, but now with one axis, which is the time, we do see the evolution of the correlations as a function of time. So we do see the appearance of very strong antiferromagnetic correlations at a short distance, and this kind of plume of positive correlation here. So the thing is kind of hard to have an intuition for. But the point is that you can Fourier transform this at every given time. So essentially, you just integrate here at a given time, and you take the Fourier transform, and you've got this kind of oscillatory behavior from which that are supposed to oscillate at twice the momentum that you are considering. As you can see here, it's not a perfect sinusoidal oscillation. That comes from many reasons. The one reason being that it's a finite size system, so essentially the spin wave kind of bounce on the edge and just interfere with the other spin waves. So it makes the analysis actually a bit challenging, but it can be done. And from this analysis, you can extract indeed the dispersion relation as a function of Q. So the square that you have here are the data. The circles are the data, and the squares are numerical simulation of the experiment for the finite size system, and including also the imperfections. So very clearly, we do observe that it's not a linear dispersion relation. If you had an infinite size system, that would be this kind of dotted line square root of Q. And if you had even a much larger system than what we have, so 1,000, so 30 by 30, you would not even reach this square root of Q. You would still have a discrepancy. So this is this numerical simulation that was done here. So now we want to do the very same thing in the case of the antiferromagnetic ordering, the antiferromagnetic interactions. The problem is that our natural interaction is ferromagnetic. So how can we probe the antiferromagnetic case? Simply by applying the following trick. Instead of preparing along Z the ferromagnetic case, we prepare the antiferromagnetic case, apply the same procedure with a pi/2 pulse, which creates an AL state along the XY plane. And now we use the fact that the highest excited state of the system is the ground state of minus or Hamiltonian. Okay? And the point is that the time evolution under H or minus H is exactly the same. And so this is what allows us to extract the antiferromagnetic dispersion relation. So we do exactly the same procedure as what we've played with in the ferromagnetic case. And when we do that, we observe that indeed there is no really square root of Q behavior any longer, but something rather which is nearly linear as a function of Q. So this is indeed the proof that this dispersion relation, because of this comparative measurement, does depend on the fact that there is a 1 over r cube interaction. So this 1 over r cube does modify the dispersion relation. And what is interesting here is that irrespective of the sign of the interaction, by playing this trick that the closed system H minus H does have the same time evolution, you can do a comparative measurement of two situations. Okay, so that's all I wanted to show you here. We've done a bit more analysis, but just to broaden a bit the scope. So we've done other experiments with the XY model, for example, not only to place them out of equilibrium, but preparing the ground state of this system. It can be done by an adiabatic control of some parameters. And there as well, on a square array, we did observe that the correlations in the ground state featured some long-range order in the case of the ferromagnetic interaction, but would feature no long-range order when you have the antiferromagnetic case, because, once again, the antiferromagnetic order is broken or destabilized by the frustration. So this is kind of a neat stuff, and in particular, the observation of long-range order in a 2D system had never been seen before. One thing that you can actually push, and I'm not going to say too much about that, but you can also use this XY interaction as a way to generate spin squeezing. I showed you that indeed you had an evolution of the correlation in the system when you place them out of equilibrium. It turns out that there is a given time for which you have prepared a state with reduced fluctuations with respect to the standard quantum limit, and that's something that we have measured. And that's again a consequence of having a 1 over r cube interactions. You wouldn't have that with nearest neighbor interaction in 2D. And finally, another thing that we've done related to that, you can actually show that if you do the experiment in 1D, so this is a ring, so a 1D chain with periodic boundary condition, you can measure that or map on this system onto what is called a Luttinger liquid. And we've been able to observe the algebraic decay of the correlation length in this system. And also that was the first time that an algebraic decay was observed on actually any 1D system. And with that, we could also measure the properties of the ground state and assess how precisely this system is indeed a Luttinger liquid. Okay, so what I want to show you in the remaining about 15 minutes is that we can extend and enlarge the toolbox by not using only 2 Rydberg states, but now 3. And in doing that, we'll be able to explore the physics of doped dipolar magnets. So this is work that we've done in collaboration with Lucas Omeyer. He was at LMU at the time. He's now in Gila. He was a PhD student. He's now a postdoc in the group of Anna Maria Rey, with Simon Allwith, who is in Harvard, and with Annabelle Bort and Fabian Grust. Okay, so here the question we're going to ask is a question that people ask a lot in the context of quantum magnetism, is what happens if you have a given magnetic background and you place a hole. So a hole means you just remove one atom, for example, and you just look at how this system propagates. So if you are in a ferromagnetic environment, nothing really special occurs. But if you are in an anti-ferromagnetic environment, you see that the motion of the hole from this position to another one destabilizes the background, which now can no longer sustain an antiferromagnetic order. So it means that you have a competition between the propagation of the hole and the magnetic ordering in the system. So why is it relevant? Because, I mean, the basic model that we have to describe ITC superconductivity, the Hubbard model, does feature this. So this is this model where you have a competition between tunneling and strong on-site interactions. And this model can actually be mapped onto a spin model using a second-order perturbation theory. And so you've got an effective coupling here. So it's kind of at zero doping, sorry, it can be done. So zero doping meaning that you have no holes in the system. And people have measured that in various systems. But if now you place holes, this is no longer, and you want to explore the phase diagram, which is supposed to be related to the one of the cuprate, you have a new model, which is called the TJ model, where you have a competition between the spin interactions and the tunneling between sites. And so this is a model which is actually challenging to solve, and now there have been a lot of progress. But the thing which is interesting is that you need a 1/r³ interaction if you want, for example, to observe these D-wave superconductive dome. So this is something that has been found a few years ago numerically. So, of course, there is a platform which is very natural to study this kind of thing. Those are atoms in optical lattices. I mean, I'm sure we'll hear from that from Markus Greiner tomorrow. So people place fermions in optical lattices. You do have this kind of effective coupling, so this super exchange coupling, 4T squared U. But the point is that naturally, in optical lattices, the interaction is nearest neighbor. And that's a bit of a problem if you want to precisely enter the phase, which is the interesting one, of D-wave superconductivity. So here, what I'm going to show you is kind of a variant where we do have the long-range interaction, so the 1/r³, but it's a bosonic version of the model. So we cannot really hope to observe the phase diagram that I showed you before, but at least it forces you to think about this competition between propagation of holes and magnetic ordering. So in order to do that and to study this, we're going to do the following mapping. So this is an idea that comes from Lucas Omeyer. We use 3 Rydberg states, okay, and they are nearly equidistant, and so state 60S, 60P, 61S, and you will call spin down and spin up the 2 states S and S prime, and the hole is going to be the P state. And so the thing that can happen now is that you've got various ways for these states to be coupled. So the most natural one is exactly the one we've described, which is this dipole exchange, where essentially you have the state SP between 2 atoms, or PS, which are degenerate, and essentially they can exchange their state, which corresponds to the hopping of spin up or spin down from one site to an empty site. And so essentially, spin up, spin down goes to the hole, or the hole goes to spin down, and this is a 1/r³ interaction. Okay, so this is my tunneling, if you want, in the language of the lattice. The hole propagates by exchanging its state with the spin that was on the other side. So this is the dipolar tunneling. Second state that we have, we can also have a spin-spin interaction, because now you've got a second-order process which allows you to go from the state 60S to the state 61S, going off-resonantly to the state PP. Both atoms are in a state PP, but each of the coupling is a 1/r³, and therefore in perturbation theory, it will lead to a 1/6 coupling between the 2 spins. So you also have an exchange here, but between the spins, and it's now a 1/r³. And finally, what you can also have, you can either have, you can have those two holes that have a van der Waals interaction, because two atoms in a p state do have van der Waals interaction, so that acts as a repulsive, in our case, hole-hole interactions. So essentially, this is all the features that we have, and so that allows you to implement a model where you've got the possibility for the hole to move across the system with a dipolar tunneling. This is the T term. You can have an interactions between the holes. That is something which is not present in the TJ model, but that you have here. And you can have a flip-flop interaction with a 1/R6 for the spins. So a bit more formally, this is the Hamiltonian that you implement here. So you've got the T part with this kind of effective bosonic operators. Okay, here. And then you've got the spin-spin part, and you've got this extra term, which once again is not present in the case of the TJ model. So the thing also which is interesting here is that you can tune those relative terms just by playing with the fact that the dipolar interaction has an angular dependence. Okay, so if you play this trick by imposing an effective magnetic field, and the interparticle distance or internuclear distance has an angle theta with respect to this magnetic field, you can vary as a function of theta the tunneling term, the spin hopping term, and the repulsive interaction term. Okay, and I should also mention that actually this kind of model has also been implemented with molecules precisely, but in their case they are very low filling, so they could not explore the physics that we're going to look at. Okay, so as time moves on, let me just skip the plumbing. So essentially we just take two chains, a chain of atoms, so we're going to do it in a one dimension, so it's a chain of 12 atoms, and we're going to change the angle of the chain with respect to the magnetic field in order to explore the various configuration for the ratios of T, J, and V's. So let's start by the case where T is nearly 0. So it means that we impose actually this angle to be nearly the magic angle here. So we are in this, at this point here. Right? And so we prepare along the chain a domain where we have 4 holes close to each other, and we've got an antiferromagnetic background. So essentially, you recognize up, down, 4 holes, up, down. And we look as a function of time at the population of the holes, so we can measure the state if they are in, of the atoms, if they are in P, or if they are in the S and S prime state. So the population here, as a function of time, you observe that this kind of domain walls that we have kind of stays, so there is nothing really happening, while on the spin sector, the S and S prime do exchange their state as a function of time. So essentially, you've got some kind of localization of the hole, while in the spin domain, there is this coherent exchange of oscillation that you can observe here. So now you vary a bit this, so you now go in a regime where T over G perp is not exactly equal to 0. And so what you see is that first this kind of domain walls start to melt slowly, and at the same time you decohere, you observe some decoherence of the flip-flop interaction in this sector. And finally, when you make a T on the larger than J perp, essentially you have a very quick melting of the hole. Some of the hole actually reach the edge of the chain and bounce back, and at the same time we have nearly no oscillations of the, in the spin sector. So in order to understand this kind of behavior, actually, we will look at what happens, the bounding of 2 holes. So let's do the following experiment where we take a chain of atoms, antiferromagnetic spin background, and just 2 holes close to each other. And so we're going to look as a function of time how they propagate. So this is a 2D diagram where we place one hole, at this location, the other hole at the other location, and after some time we look at where the holes are. So this is the correlation and the probability to find the hole at site I correlated with the fact that it's at site J. What you observe is that actually the correlation is always parallel to diagonal, nearly. So it means that actually the 2 holes propagate correlated, so close to each other. So that's kind of a proof that actually they stay bound during their propagation. How can we explain this binding? Well, simply by energy conservations, by the fact that if you want to move your hole, or to break your hole, your hole pair, by placing a spin in between, it costs you energy. What energy does it cost you? Precisely the V, which is the whole interactions, but also the fact that there is this GZ interaction in the spin sector. It comes from the fact that you're breaking the antiferrometric order between two neighboring spins. So this there is an energy mismatch, but there is still a tunneling that allows you to go from this to this and back to this. And the propagation of the hole, therefore, corresponds to a second order process. And you have an effective tunneling, which is just T squared divided by the energy difference here. OK. So this means that indeed, and the more holes you put, actually, it turns out the heavier the kind of this cluster of hole is, and that's the reason why when you have 4 of them, they actually nearly don't move. One thing that I want to show you, and that's interesting in the context of what I mentioned for ITC superconductivity, although those are bosons, is the fact that we do see the influence of the dipolar tail of the interaction. Because what I showed you is kind of a nearest neighbor interpretation of the propagation. But of course, to go from here to here, you can either go this second order route, but you can also go the direct route where actually these holes jump over the first one and reach there. And that happens with an amplitude which is T/8. So at the end of the day, you got the interference between the second order tunneling and the effective and this long-range interaction coming from the dipolar tail of the interactions. So we can do that by simply changing the angle of the chain and therefore explore the case we've got positive or negative tunneling, and that should reflect in the fact that T effective is either smaller or larger. And so this is what we observe here. So we measure the position of the center of mass of the holes as a function of time. And we observe that indeed, depending on whether you have negative or positive tunneling, which is to say positive or negative interference in the effective tunneling here, you have a difference in the propagation. So that's the signature of the influence of the 1/r³ tail. OK, I think that I should probably try to stop here. So I will let me go to the conclusion. So I just try to show you that here, if you enlarge these, the atomic structure by going from 2 states to 3, you can implement richer spin model. The kind of physics that we are actually looking at the moment is called kinetic frustration physics. So we look again at the propagation of holes and magnons, and it turns out that they form a pair which is bound in this kind of ladder geometry. So this is something we're exploring at the moment. And because it was mentioned earlier this week, the spin liquids, I mean, that's also something that we are writing up. We've been working for nearly 3 years now with Norm Yao towards the observation of a Dirac spin liquid in this system. So essentially, you have this XY interaction on a Kagome lattice. It should be a Dirac spin liquid. The problem is that the experiment is hard, first. And second, it's not only that we are bad experimentalists, it's also that we need a better theory criteria, positive criteria, to decide what is a spin liquid. I mean, none of the ones proposed so far can be easily measured in the lab for this U1 spin liquid. OK, and with that, I would like to thank you for your attention.
Questions?